construction analytics and big data analytics, and how, let's say, something like point clouds can actually be considered first as big data, and then how would we be able to manage it in order for us to be taking some sort of information with respect to construction analytics from that. Okay, so we've talked about how, let's say, our whole process of construction monitoring and control is carried out, right? We said, okay, if there is going to be some sort of deviations between the planned and the actual, that deviation needs to be first measured and then compared with the actual. And if there is any deviation, that needs to be identified and improved. And we said, for instance, in this case of the competition pool, that, for instance, there was some mismatches with respect to the dimension. So there's some quality control issues. And with respect to that, we were able to utilize point clouds and laser scanners to be able to extract that information. Once we have that information, we would be able to extract that information and gather what we want in terms of our key performance indicators. In this case, our key performance indicators is basically whether the dimension matches together with the tolerances between the point cloud, which is what has actually been built, and our BIM or whatever digital model that we might have, right? And we also mentioned that this goes hand in hand with our cost influence curve, right? And what that means is that as the construction or the project life cycle increases in terms of its time, our degree of influence that we have on a change is going to decrease and the cost of influence is going to increase. So what that means is whatever type of deviation we're trying to measure here, the earlier we identify it, the better it's going to be. Now, how can we guarantee that we are going to identify these deviations earlier in terms of data collection perspective? How can we guarantee that? Or how can we basically reduce and mitigate the risk of late identification of deviations? Any ideas? So if we want to identify deviations as early as possible in terms of data collection, can we? Regularly, exactly. So the frequency of data collection becomes very important, right? That means that the more frequent we collect the data, the better chance we have of detecting what these problems could be early on or at the time that is going to be taken. For instance, if we do it every 4 weeks and a deviation is occurred at week 1, what is going to happen? We've identified this 3 weeks later, whereas if we were doing it every week or twice every week, we would be able to identify it much better with much more accuracy and much more frequency. So here the frequency becomes very, very important for the timely identification of these deviations. The second part of it is how well we would be able to analyze this data, so the accuracy of the data, and how well we would be able to basically utilize that information to get our KPIs from that, okay? So here, the frequency and the reliability of the data collection and analysis is key for us to be able to do that. So now what happens? We have point clouds, we require it frequently. Let's see what the characteristics of point cloud is. So point cloud is basically a bunch of 3D coordinates of our surrounding areas. If we utilize, let's say, terrestrial laser scanner or something like this, every part of the project, every surface is basically represented by a bunch of points, okay? What do we have to do? We have to analyze these points in a way that we would be able to identify what those surfaces are, and then whatever information we want from this. For dimensional compliance, we need to be able to identify how well the surface and the dimensions of the object is going to comply with our plan. In terms of progress, we need to see whether that particular object is observed and present on site. So with respect to different information that we require, we would require different types of, let's say, processing of this point cloud that we want, okay? But what does that mean? That means that we still need to collect this and we need to analyze this. Now, in terms of the data itself, you have about 1 million points per second that you're collecting. Every, let's say, monitoring time that you're doing is going to be around 1 to 2 billion points. 20 to 40 gigabytes every time. Let's say you're doing 10 different monitoring locations, okay? And if you're doing 10 projects in 10 days, this would be 2 to 4 terabytes in 10 days. See, it accumulates very, very fast, right? So now there's going to be a give, right? How frequently do we want this information, right? Versus how much risk we have or are going to be accepting for if there is some mismatch, that risk is going to be accepted, okay? That's what we're basically sacrificing here. There could be a possibility of a mismatch, there could be a possibility of a discrepancy, but because of this large data, we would have to basically manage that in that sense, okay? And with that being said, point cloud is one of the types of data and construction projects that will be and is actually identified as big data. Now, what this means is that this big data needs to be somehow managed in order for us to be able to get the construction analytics that we want from it, or the information that we want from it, right? And what we still want is to be able to manage this while being able to have frequent data collection, because we do not want to sacrifice that. And that is basically the area that we want to improve. In reality, we might need that, let's say, every day, but in reality, for practical reasons, we might get this information every 10 days, right? We want to be able to see how we can utilize technology and different strategies to be able to still maintain this one every day that we require, or as frequently as possible, without sacrificing in terms of the data management and various different aspects with respect to that, okay? So let's talk about what type of analytics we can do and what is the process of preparing our data in order to basically gather the information that we want from it, which really is our key performance indicators that we want. So we have some data, we need to process that data, analyze that data, prepare that data, and then get whatever information that we want from the other side of it, okay? So some examples of these, we talked about, for instance, how we can utilize field information modeling to be able to get the point cloud, our 4D BIM, and then identify the status of the project with respect to the progress and dimension. We also talked about, for instance, how we would be able to perform, let's say, point cloud processing to be able to get dimensional verification, as well as, in this case, for instance, static displacement monitoring. Or in terms of industrial construction, we talked about how we would be able to utilize point clouds to extract the information regarding the flanges and basically these modules before they are basically shipped to site, because the locations of these flanges becomes very, very important for us. Why? Because this module is going to be built in a factory. It's like almost the size of this room. Then it's going to be shipped to site. When it's going to be shipped to site in, let's say, minus 30 degrees in Canada, we need to know that these locations of these flange, which these pipes are going to be joints, are going to be in the proper location. How can we guarantee that? We need to be able to basically get the point cloud, extract the information that we want from it prior to it going to site, verify that. Once it's verified, then it could go ship to site, and then over there, they would basically be able to be matched, right? So there are some ways that we would be able to extract information that we want from these point clouds of construction elements in order to get information that we want. So what is the process of preparing our data in order to be able to even start with this? So there's some typical steps in big data analytics. One that was basically specified by Microsoft has 4 real steps. You collect the data, you process the data, scrub the data, and then you analyze it. So in our case, what does that mean? That means that we collect the data. Our collected data is point clouds, right? Using laser scanners, using photogrammetry, whatever method. Then you have to process this. That means that you have to summarize this information as much as possible to what we want. In this case, for instance, I have a bunch of planar surfaces. I need a process of automatically extract planar surfaces from these point clouds. And now my point cloud has been summarized into a set of planar surfaces with some boundaries around okay? Then the second part of this is the scrubbing. Here, what I would say, the scrubbing is how much detail we're going to be basically needing in terms of our KPIs with respect to what has been planned. So how do we want to summarize this information? How are, let's say, these elements identified? What it is from our plan and from our information that we want that we need to be able to extracting there. And this scrubbing is basically coming from our plan side and from our BIM side. Then these two needs to be basically joined together through some analysis so that we can finalize those deviations that we want here. Okay, so this is the process of big data analytics for the preparation of the data in order for it to be utilized for construction analytics for us. Now, I'll give you examples of how this could be utilized in earned value management in order for us to be able to basically get the information that we want from it with respect to different levels of analytics. So there are really four main types of analytics that you can perform. Does anyone know what those are? Never heard of it? So we have four major ones. One is descriptive analytics, okay? The second one is diagnostic analytics. Yeah. The third one is predictive analytics, and the fourth is prescriptive analytics. Descriptive means that we want to describe the data that we have in an understandable fashion. As an example, earned value analysis. If we can actually get all of the data into one simple curve that would provide us whether we are going to be ahead or behind schedule in an overall project duration, that is going to be an example of a descriptive analytic. Let's talk about diagnostic analytics. That means how some, let's say, deviation has happened. This means what type of activity and why that activity was, let's say, behind schedule. A predictive analytic means what kind of prediction can we actually get? What type of method that we can utilize in order to predict the data and the pattern of the data, let's say, based on previously identified data that we have, how can we actually predict what's going to happen in the future? And then the prescriptive analytic, that means what type of prescription can we actually provide to this, let's say, disease that we have, which is, for instance, in this case, it's going to be delay in construction. What type of actions can we actually take and we can prescribe in order for us to meet the deadline? So I'll give an example as we can go with these four types of analytics using earned value analysis and point clouds. So we've talked about, for instance, we have every time that we monitor it, once we monitor it, we go through all of those processes of collect, analyze, collect, basically process, scrub, and analyze, right? We go and we get basically to this point. Once we get to this point, we can utilize that information that we extract to be able to develop a descriptive analytic of the status of the project. In this case, earned value analysis for delay. If we talked about this, if the budgeted cost of work performed is less than the budgeted cost of work schedule, what happens? So if our work performed is less than the work scheduled, it's a delay, right? So we would be able to identify this in project level in a very simple description, how it's going to be performing, right? What about the why, or where is this particular problem happening? When you go back, and we would be able to actually see the type of activity that there's going to be some delay, this is a type of diagnostic analytics, meaning that we can actually go and find the source behind this, of why this has actually happened. Now, there are other aspects to this as well that would be different levels of analytics that you can get. For instance, exactly why this activity also was delayed. Some of it would be able to be identified through point clouds. Some of it would not. We need additional data, right? But in terms of what we can get from point clouds, at least we can find the diagnostic of what type of activity was actually delayed that caused this overall project delays. Then we can go and look further into it, right? Now, let's say we go and we monitor it again, and based on the information that we have from different stages of monitoring, we can now go and predict what our budgeted cost of work schedule could be going forward, or the budgeted cost of work performed would be going forward based on the previous data that we've collected. This is a type of predictive analytic. Given previous information to predict what is going to happen in the future. Now, let's say at this point that we've identified that if we have delays based on previous projects as well or similar situations, we have an action plan. I'm going to hire an additional crew member to basically work on the elevator shaft. Now, once we find this action, so that is going to be an input of an action, what is going to happen? We then measure the response of that action. What does that mean? I've taken an action. How well does that action match with what my objective is, which is to meet the project deadline? Okay? In this case, this particular action has had a positive outcome on our project. What does that mean? That means that we can now have an action plan that we have and a response. When you have many of these available, then we can actually prescribe a particular action in case we have similar circumstances that happen, right? Which is a type of prescriptive analytics. Because in this case, once we do it on multiple occasions, using this action, we now have an action that is related to some outcomes, right? So later on, similar situation could happen, and we have many of this data. Then what we can do, and many different actions, then we can decide which one of these actions we're going to be taking in order to satisfy and solve the problem that we've had. So essentially, in theory, if we can do this in many projects, if we can actually utilize point clouds for this in many projects as frequently as possible, and we can have our action plans when we take actions measured as well, we can actually relate all of these together in order for us to create a closed loop of our descriptive analytics, our diagnostic analytics, predictive analytics, and prescriptive analytics as well, so that we can utilize it for the future. This is one example of the benefits and how one simple data, together with some minor, let's say, addition of different types of, let's say, actions that we would take, could actually support our data analytics as a whole. Make sense? Yeah? Okay. So what is the real challenge? Why is this not being used? Why are we not basically taking this? Well, obviously, one is with respect to the amount of data that exists, right? But then what is the real bottleneck here? If we have many data, then we would have to automate that, right? But the bottleneck is exactly in the automation. If we want to do this manually, obviously, we've also talked about it, that all of these elements, every time that you're basically measuring it, how are you going to be able to even extract the information? And you guys did one example of that particular column that we did, right? In a more semi-automated way, how long that took. Imagine you're doing this on different construction sites or on the same construction site multiple times. It's going to take forever, okay? So it's not practical in terms of its time consuming. That means that with respect to even taking out of the consideration the amount of data that we have, it's just not possible to process that information and analyze that information on time to be able to utilize that information. If we're getting it every day, but our processing is going to take 2 weeks, it's not going to be even useful, right? And that's what's important here. The other side of it is also with respect to the subjectivity, and we talked about the fact that if we have, for instance, the same set of points that's, for instance, on the top right there, rebar, that I gave to 6 different colleagues of mine. And what they provided were basically different selections of these points, and every time that you fit a cylinder to it, it gave a different result, and that is different from what you can get analytically from these results as well. That means that the processing of it also becomes subjected to the person that is analyzing this, and we want to reduce that subjectivity as much as possible. And this is a prime example for automation. So if we can, yes. You mean the sizes of these? Yes, yes. So this has, I think, like a centimeter or less in terms of its diameter. This was like 2 centimeters. So it was like almost you know, I would say maybe from the minimum to the maximum about half an order of magnitude, maybe like 5 times more. So you go maybe 2 to 3 or maybe maximum 5 times, but it was considerable. Why? Because especially when you have missing data, you're going to have problems with that. Because if you have a missing data, then you would have to really model it in a particular way. Now, if you're basically extracting that, and if you don't extract it properly, it's not going to give you the full picture. As an example, this was, for instance, a project that I did, and I'll talk about this as well. One thing that there's a problem. If you have, let's say, an ellipse, and if you have data on only this side of it, the possibility of you having to fit an ellipse to this would be the actual ellipse. This would likely be the ellipse that you're going to be fitting to this. This is the deviation that you're seeing there. Meaning that if you have outliers and if you have biases in the locations of these, that would create problems. Now, if you can actually reduce this to another point here, this would be something that is going to be, let's say, closer to this. So it's going to be a bit closer. So dependent upon which points you're selecting, you're actually dictating what your model is going to look like. And that by itself, we can actually analytically extract, especially the ones that are geometrically, you know, easy to identify. You can actually analytically extract that. But yes, in this case, it was very significant. I mean, from my side, maybe my example was a bit biased because I wanted to really show that there's a, you know, there's a disparity there. But it doesn't change too much, you know, what it is. At the end of the day, we are looking for millimeter or sub-millimeter deviation, but even from one person to another, you might get, let's say, a 5 millimeter deviation. If we can reduce that as much as possible, remove the subjectivity, that is basically where we're going to aim at. So manual intervention in this case is also subjective and prone to human error. So what do we get? Right now, we have identified that point clouds are frequently required, repetitive task, challenging to process manually, and it's a non-production activity. No one's going to pay you for basically going through the point cloud and assessing whether what you have built is matching what the reality has been, what the plan has been. Why? Because really you get paid for production activity, to produce something. You don't get paid to recheck your own work. If you can minimize this, now that doesn't mean that it's not valuable, because if you have a mismatch of some sort, discrepancy, and you can identify it earlier on, that's much better than identifying it later on, both in terms of liability and in terms of meeting the project credentials, right? However, it's generally a non-production activity. So these are basically the aspects that are going to be dictating that our particular problem of point cloud processing is a prime candidate for automation. Repetitive, non-productive, frequently required, and challenging process manually. So now we have a system that provides big data, and we need a process to be able to minimize as much as possible the challenges with manual intervention. So we need to automate. So I'll give you two strategies that has helped me in my life to manage these point clouds as big data by means of aspects of dimensionality reduction as well as devisement of a monitoring plan. So we go and talk about the construction analytics and the preparation steps for point clouds. We have the collect, which means that if we can reduce as much as possible the number of points that are required, as well as the time it takes to collect this data, that by itself can improve our overall, let's say, processing. So let's say that I have no plan, but I think that if I have a point, let's say, scan station here, scan station here, scan station there, that is going to basically give me as much data related to what I have, in opposed to having an optimal number of scan stations that would give you as much information and data that you really, really require and nothing more. So this optimization can benefit significantly the next steps as well. Then the second step is, how would we be able to utilize dimensionality reduction? What does that mean? We are looking at three-dimensional points. If we can reduce the dimensionality, this by itself can reduce considerably the processing times and the analysis of it, and it simplifies our problem. So these are the two strategies that I'm going to be discussing with you. The first, developing a monitoring plan. So we have to devise a strategy to simulate what point clouds look like before going to site. Why? Because we have some digital model that we're going to be utilizing. Inside of this digital model, we have different information that we have from the type of material, texture, various things, depends upon the level of detail and development that we have for that particular model, okay? Using that, what are we going to be getting? We're going to be getting where we're going to be placing these point clouds or these scan stations in order to acquire the point cloud that is going to be as accurate as possible and covers all of the elements, right? And provides us with the information that we want, let's say in terms of the density and various aspects, okay? So we go and how many of you guys have played these first-person shooting games? When I was in high school, this was a very, very popular game called Counter-Strike. Very, very interesting game as well. But basically what it is that you have a line of sight between your gun and that crosshair that is there, and whatever surface that is going to be there as well. This strategy, which is a raycasting strategy, can be employed to simulate point clouds in basically a model that we have, because this environment is also a model, right? A digital model, and we want to make sure that when we basically shoot the gun, it's going to exactly go with a straight line into that particular location that we want. So here we can utilize the same strategies in order to simulate the point cloud at a particular location. So what does that mean? If we have a particular location inside of our model, we would be able to identify the point clouds that is going to be generated if that particular scan is in that particular location. This in terms of the density as well as in terms of coverage and in terms of accuracy, because we can model all of these. Now we can remove it and move it to another location and get a bunch of other ones. What do we want? We want a combinations of these stations that would basically give us various different aspects, meaning we want to minimize the number of points. That's the major aspect that we're looking for, while minimizing the number of stations, maximizing the accuracy and maximizing the coverage. That's what we're looking for. So this is a prime example of an optimization problem. Once we can identify the function that would be able to provide us this, then we can utilize various methods, including artificial intelligence-based methods. And in my case, I use a quadratic, unconstrained binary optimization, where you can actually use that type of a method with some let's say, adjustments inside of a quantum computer as well, and would give you very, very good results. But at the end of the day, what you would get is something like this. We have a site like this, and these are the optimal locations that it would provide. When you're looking at it, this wouldn't necessarily be the optimal locations that you would think would basically provide you the minimum amount of, let's say, occlusions, maximum coverage, best density, and the best accuracy that you're going to be getting. You can mathematically identify it, optimize it. Once you have these locations, then what you would have to do, if you want to minimize as much as possible the time that it takes to basically gather this information. Once you do that, we have a topic called the traveling salesman problem. Have you guys heard of that? Yeah. So then you basically provide it with a traveling salesman problem, and then you mobilize this robot here, Spock, and then that would be able to collect the information that you want from the site, right? So this way, if we have a monitoring plan where now we can utilize computational methods and optimization methods together with our digital models that we've modeled very, very accurately, and we want to utilize this as much as possible to be able to identify the locations that need to be visited and the scan that needs to be carried out, and how or with what, let's say, order these stations need to be visited. And if you have multiple of these, then you can basically solve, based on these locations, the multiple traveling salesman problem. That is a more complicated problem, but you can still, there are still methodologies that would be able to do that, especially with genetic algorithm, you can get a good result. So this is one way that you can reduce the number of points, number of stations, and the travel time required for this. So you can get exactly what you want from your point cloud and nothing more. Let's say you only want to identify the column, let's say dimensions of this column and this column. You can remove all of the other ones. You can identify what point clouds are required for that particular. Okay? The second one is with respect to our processing and analysis, right? Essentially the processing and the scrubbing. So one thing that I'm going to be talking about is dimensionality reduction. Meaning if we can basically simplify our problem, if we can creatively think of a solution that could reduce the dimensions of our problem from 3 dimension to anything less than that, that would be significantly beneficial. Why? Because now we're computing on a lower number of dimensions. This by itself would reduce the computation and would reduce the burden of managing point clouds as a big data as well. So I'll give you 2 strategies with this. The first one is the floor detection. So if you have a leveled laser scanner in a particular place, it's going to be leveled. You know that there's going to be leveled with respect to the gravity, okay? This by itself would provide the opportunity for us to identify what the floor and the ceiling is going to be. Why? Because for a, let's say, a room like this that is going to have a floor and a ceiling, if you take a look at the histogram of point height, there's going to be 2 peaks. One is going to be on the floor and one is going to be on the ceiling. And actually, this is going to be your assignment for next year, if you so chose to do the field information modeling class. This is going to be one of your assignments, is that, as you can see, if you move it into that direction, you're going to have a lot of points on the floor and a lot of points on the ceiling without change or significant change in its height, right? Why? Because you have, what is the points on the floor? Points on the floor are the points that have the same height, right? Because they're all on one floor, right? And the deviation that you see here is basically the random measurement error that you're going to be seeing going up and down for that particular point. But they are going to be similar to the normal distribution. They're going to basically distribute themselves in around a median, right? So you have these points on the floor, these points on the ceiling. Now I can identify all of these points from the floor and the ceiling only using the height. So 1 dimension. I can gather all of this information and all of this information. And you see from these, this part and this part are much more than all of the rest, right? So in many cases, for instance, in rooms or especially on construction site when you don't have, let's say, envelope walls yet still built, you just have skeletons, really the majority of the points that you're going to be having is the floor and the ceiling. And next semester in the field information modeling, you're going to be seeing this very clearly using the point cloud data that I will provide to you. That if you just have these columns and you floor and the ceiling, the majority of the points is the floor and the ceiling. So because of that, and because of the fact that we are removing, let's say 80 to 90% of the points at every time, using only one dimension versus the three dimension, if we want to compare it, that would be around 15 to 25 times different in terms of its computation. This means that if it's taking 1 day versus 15 days, you see, it's huge. Just by simply defining the problem, changing the parameters, and thinking about it a bit more creatively by reducing the problem's dimensionality. Make sense? Over half of all the points are removed. In these cases, it could even be 80%. Half is typically in a room like this that is removed. Even I have examples of these tables. You can actually remove these as well. It would be somewhere like here. It's not going to be as much, but it's going to basically show somewhere in the middle here. So you can even remove the tables because they're more or less the same height. That's just something interesting to know as well. So the other one is the case of pipes. So pipes are cylindrical elements. Again, by going back to its design and how cylinders are defined, any cylinder and any randomly oriented plane, if they are intersecting together, and we take the points that are closest possible to those particular planes, it's going to give you an ellipse. Now, the problem of cylinder detection in 3 dimension is going to be reduced to determining ellipses in 2 dimension by basically going and projecting the points that are close to this surface onto the surface, let's say within 1 centimeter of it. Then we are defining and determining what the ellipses from those particular points. So now there are 2 benefits here. One is that I'm only taking a look at points within 1 centimeter of this. That is significantly reducing the number of points versus just looking at all of these points at once and going and finding the cylinders, right? This by itself is, and the second part is that I'm actually looking at it in terms of its in 2 dimension versus 3 dimensions. So both of these together have a significant impact on how well and how easily I would be able to identify the cylinders from this. Once I have these, I would be able to use these very, very old, let's say this is from Dandelen's spheres that has proven what the relevance between the dimensions of those ellipses are with the basically parent cylinder, if you have the normal vector of the plane. And this is, it was solved in like the 1800s. So you can use this information to get initial parameters of what the orientation and the direction and the radius of your cylinder is. Then after that is going to be, for each and every one of these is going to be a cylinder that you have. Then you're going to be finding what would be the best cylinder with respect to that. So you're only going to be selecting those points, and then you're fitting a cylinder to that. It's a very simple process after that. The problem is weeding out where these cylinders are. That is the major challenge here. And then you would be able to extract and get them. Computation time, because of the fact that we're only dealing with small number of points, let's say you have in the order of, let's say, 10,000 versus, let's say, 10 million or 20 million. And the fact that you're doing it in 2D versus 3D. Both of these are impacting this significantly. And then you would be able to utilize this for various different aspects, for instance, pipe detection and classification, as well as using this for other analytics as well, as you can see here for progress reporting for pipes and how much pipe has been laid. Yes.
Those dimensionality reductions, they have to be done manually again, right? Or can they be
Which part of it?
All of it? Or maybe you have to define the plane and
Okay, yes. The plane part, at least the way that we've defining it here, that part can be manual very fast, right? You basically, the only thing that you need to do in your software is take 3 points and then it would cut a plane. That's it. In 3 different cylinders, and as long as that's the case, it would cut it. There are methods that you can automatically identify that as well, and that's very, very simple as well. In the other part is that if you have, let's say, cylinders that are typically in, let's say, industrial plants, they're in the 3 dimensions. So that would be very easily identified that, you know, you go 1 vertical, 1 horizontal, and then, you know, 1 just randomly oriented, and you would be able to identify it fine. But even if you do it manually, which is only requiring 3 points there, what you would get is really identifying each and every one of these. But yes, that's the one part that might require a bit more, let's say, intuition to be able to automate the process of selecting the plane that would be able to cut these. But if you don't want to do that, it's very simple. This part, again, it's algorithms that you have to use to do that. However, you're going to do it from this part going forward, what you're going to be getting is simply this. You are now reducing the problem of cylinder detection in 3 dimensions into ellipse detection in 2 dimensions. It's an easier problem to solve, and it's basically reducing your dimensions. For this, I have algorithms that automatically would be able to do that, no problem. I actually, for this as well, I have algorithms to do that very fast and very effectively as well. And this by itself might reduce this to more of a 5 to 10 times if you want to do this part of it completely automatically with no prior knowledge of where the orientation of these pipes are. It would still be considerably better, but it wouldn't be as, let's say, fast. But if you just do the 3-point selection, it's very fast.
And is there already a software that implements those functionalities?
I guess you have to take next semester to be able to do that. You mean from my side? Yeah, I've developed these myself. Yes. Commercially, I haven't seen it yet. So yeah, these are published in very, very reputable journals as well. This work was published in 2021. I've even improved it slightly, you know, right now in terms of computation time too. But in terms of whether this process is being carried out right now in softwares, no. What a lot of softwares do right now is basically you can give it the point cloud, and it would give you the cylinder detection directly from it using the normal vector that is computed from the point cloud. So this by itself means that it has to compute the normal vector, which is going to take time, and it's going to be classifying the pipes based on the directions of the normal vector. Where if you remember, we talked about the principal component analysis for plane detection. For cylinder detection, you can utilize principal component analysis similarly, but it's a tedious process, right? And this would reduce it significantly. So this is, I mean, I'm personally surprised that not a lot is happening in this area. Perhaps I should start my own company and build these myself. But that's basically what you're going to be realizing even next semester as well, if you choose to take this course, the field information modeling. Essentially, what you would get is a very clear understanding of how or where a lot of these softwares are actually at and what type of work is necessary to do this. You know, but even small bits and pieces. And how I envision it personally is more or less in a semi-automated way, not a fully automated way. The modeling of this can be simplified and automated very fast. Instead of right now, you go into the software and looking at each and every one of these pipes, you just say, oh, there's a plane here that is going to cut these pipes. And the software calculates all of these, and then it gives you this, and then you as a user can say, oh, this and this are not actually pipes, or they're not cylinders that I consider as pipes, and you remove it as well very fast. And then whatever that loop is going to be used for future, let's say, machine learning as well. So there's an envisioning of this with respect to your ability to essentially work with the software, and the software starts learning the more input that it gets from you. And that's how I envision it. It's still not there for some reason, but yeah, that's I decided to come and start my academic career rather than going into this direction, but I had a lot of ideas in this field too. So from historical data, you can now use this in your predictive analytics, right? If you have 50 different times that you've collected this information, you have different types of, let's say, information with respect to progress. Now you can use to say, okay, if I have progress in this way for similar project, what is going to happen in the future? So the more data you have, the more chances you have in predicting what is going to happen, because then you can basically find the patterns, right? Okay, so what do we learn? This is the wrap up of this course: point cloud preparation, collection, process, scrub, and analyze. Types of analytics. We talked about point cloud, 4D BIM, analytics, and then we talked about how we can utilize earned value analysis to get our descriptive analytics, diagnostic analytics, predictive analytics, and prescriptive analytics, or what steps are necessary to do that. Then we also talked about the two strategies that I would like to, that has helped me significantly in being able to reduce as much as possible or deal with our big data analytics here. The first one is optimal monitoring plan, is to find the locations and the order and how you're going to basically manage and identify the location of each and every one of these. And then the second one is the simplification by means of dimensionality reduction and understanding the problem by itself, right?